Thank you very much for this invitation. Děkuji za pozvání. So I will give a very basic talk on infinite dimensional geometry. This research is financed by Austrian grant, which is called Banach-Poisson-Lie groups and integrable systems. This will not be the topic of today. Yeah, it could have been so, but I decided to do an overview talk on other application of infinite dimensional geometry. Let me start with an advertisement on a thematic program that we are organizing in the Schrödinger Institute with a topic infinite dimensional geometry theory and application. So there will be 5 weeks. From very general infinite dimensional geometry to very applied ones, so shape analysis and medical applications. And today I will give you a brief overview of what we can do with infinite dimensional geometry for shape analysis. Why are we talking about infinite geometry? So I apologize for those who have seen this talk before. But okay, so why infinite dimensional geometry? I have to advertise a bit. Well, one reason is that most shapes that we see are infinite dimensional. So if you look at 2D surfaces that can vary, so for instance, horses, cats, or any 2D surface, with a deformation variability, then you end up with an infinite dimensional manifold, which is a manifold of 2D surface in R3, or it can be any other type of manifold where you have an ambient space and a manifold inside with a variability. So typically this manifolds, so not the surfaces themselves, but the set of all surfaces in R3, for instance, form an infinite dimensional manifold. Natural objects also on finite dimensional manifold. We have seen today vector fields, distributions, and if these objects are varying or Riemann metric, we were talking about Riemann metric conformal classes, all these objects are encoded as section of some finite dimensional vector bundles, for instance. So these form infinite dimensional manifold in general. So here you see, for instance, a cat, and we will go back to this picture a bit later. So the green arrows that you see on the cat are just vectors located on the surface of the cat. But 3D vectors. So you imagine your cat inside the ambient space, the 3D ambient space, and you're thinking of deforming your cat. So you can follow these green directions to deform your cat. But you can also decompose this vector field into 2 different vector fields, one tangent to the cat, that's the red one, and one normal to the cat. And you will see this decomposition a bit later. So this is, for instance, a space of vector fields on some 2D surfaces, which is an infinite dimensional object. Oh, there is a missing picture here, apparently. No worries. Yeah, and even for finite dimensional geometry, infinite dimension geometry is important. Basically, the existence of geodesics on a finite dimensional manifold comes from so either so it's a minimization procedure, for instance, to geodesics are a solution of a Cauchy problem, if you want, or minimization of the energy gives the geodesics. So in both cases, so either the 2-boundary value problem given by this geodesic between 2 points, is a minimization problem in an infinite dimensional manifold of curves. Or if you start with an initial value at the point and velocity, then you have a Cauchy problem, and you know that its existence of the solution comes from a fixed point theorem using a contraction on an appropriate infinite dimensional space of curves. So in both cases, a finite dimensional geodesic or finite dimensional manifold comes from either a variational principle in infinite dimension or a fixed point theorem. I mentioned this before. If you want to vary some geometry on finite dimensional manifold, Riemannian matrix, complex structure, symplectic forms, then usually the space that you get is infinite dimensional. There are more to this, so I like to mention this because it's a non-trivial example where, as far as I know today, we don't know how to get a finite dimensional structure without using infinite dimensional geometry. This is an example of a hyperkähler structure on complex coadjoint orbits of complex Lie groups. So we know in the symmetric case for Grassmannians, we know how to get it without using infinite dimensional geometry. But in the general case, for general complex coadjoint orbits, we need the space of solution of NAM's equations and the action of the gauge group there. So it's an infinite dimensional symplectic quotient that gives a hyperkähler structure on space of coadjoint orbits. So finite dimensional object at the end. So this was one example where infinite dimensional geometry is important. For today, I will just advertise this topic using quotient spaces, and I will go into Riemannian structure on quotient spaces and present 3 different methods that you can use to endow a quotient space with a Riemannian structure. It's very natural. All 3 methods have advantages and disadvantages. I will give example for in the case of shape analysis of surfaces and curves. Don't hesitate to ask questions. I'm here for you, so if it's not clear what I'm saying, I hope to make it very basic, but if it's not the case, please ask. So I will start very easily, action groups on shapes. You see here different ways you can act on contours. Here are the Statue of Liberty. So there are different groups. I take some examples of R2 by acting by translation on a shape. So you can think of the orbits of one element in different ways. So, for instance, you can think of the orbit by translation as all the shapes that you can get by translating one given shape in your plane. So it's like all the possible elements of the orbits. That's the first. Do you see my pointer? No. Okay, I have to point here. That's better. So you can think of an orbit as the set of all possible elements in the orbit, like here by translation, here by rotation, here by scaling. That's a possibility. Or you can choose one preferred element in your orbit. So that would be like choosing a section of your quotient space. Here you can choose, for instance, the center at the origin. Here the curve is here parametrized. The curve starting at the origin. That's for the translation part. For the S2 action, you can just align your shape, supposing that there are 2 principal different axes. You can align it with a frame that you have chosen, or you can start with a tangent vector starting horizontally. These are 2 different sections of the same quotient space. And for the scaling, you can either get a length 1 curve, or you can choose to enclose an area of one. So 2 different possibilities for the scaling. And again, you can do, this scaling is here again. And what we will be interested in is the orbit by the group of reparametrization of my curve. Here are parametrized, so there is a starting point, an end point, which is the same, and the curve is parametrized by 0, 1. So of course, the group of diffeomorphisms of 0, 1 acts by reparametrization of the curve, and if you have a sampling of this curve, if you act by reparametrization, you will get another sampling, so another disposition of the points along the curve. And you have many choices for this. So arc length parametrization means, for instance, that the points are distributed uniformly along the curve, but you can choose another kind of parametrization. I will briefly mention curvature proportional parametrization in this talk. So where the points are located where there is a lot of curvature, which allows a sparser encoding of the curve. Yeah, let me go back. I have to point here. Okay, yeah. So just to summarize here, we have different ways to understand or to represent quotient spaces. Either one element of the quotient space will be the set of all elements of the orbit, or we can prefer one representant. This would be a section. The space we are interested in are shape spaces, surfaces, for instance, here. And we want to deform them because we want, for shape analysis, to quantify the deformation from one shape to another. And we will do this by introducing Riemannian metric on this infinite dimensional manifold of shapes. So here there are 2 different important manifolds. The pre-shape space are the space of all embeddings from, here are genus 0 surfaces. So the model space is the sphere, S2. We embed S2 in R3, and the image of this map will be either a horse or a cat or whatever. So these are smooth embeddings. And, but what we're really interested in for computer science is the shape space, so without parametrization. So this is a space of 2-dimensional submanifold of R3 without any given parametrization. Okay, so but we will use parametrization because it's very convenient for entering the shapes in a computer. Basically, these are matrices, and we just display the shapes. So you see here different parameterization that are encoded with these grids. So this is the grids. This is the image of the spherical coordinates on the sphere. There is a north pole and a south pole somewhere. One is red, one is blue. So different encoding here coming from different parameterization of the same shape. And we want to measure a deformation from one shape to the other, but independently of the parameterization used in between. The parameterization is useful for the computer, but we want the analysis to be independent of it. So for instance, if you see what we are interested in, we want to measure the blue deformation. So if we just forget about the parameterization, we want to measure this deformation independently of the parameterization. So any lift of this deformation, it would be nice if it gives the same result. And we will see that a Riemannian setting, we will see this in a moment. So let me just mention that shape spaces are naturally nonlinear manifolds. So as mentioned before, these are parameterized shapes, so we know where to put the point to draw the shape. But if you take two arbitrary parameterization and you want to linearly interpolate them, meaning that you superpose your two shapes and you join just point number one with point from the first shape to point number one in the second shape, you get garbage in between. If we started with arc length parameterization on the left and an arbitrary parameterization on the right. If you start with two arc length parameterization, you get something a bit better, but there are non-natural things happening here. What we want to do is a bit more geometry so that interpolation gives good results, for instance, at the level of the legs here. So this is one kind of possibilities. I will go back to this later. Yeah, so I was mentioning Riemannian metric on a quotient space. So if you are a geometer, you will encounter probably a Riemannian submeasure theorem. Let me mention that here we are interested in an infinite dimensional setting. And there are still questions around this theorem in the infinite dimensional setting because basically, if I go back, for instance, oh, yeah, no, here, I'll go here. Yes, so here I was mentioning that I'm decomposing the space of vectors along a 2D manifold into normal direction and tangential direction. This works well in this case, but generally in infinite dimension, you may not have, you may end up with spaces that have no complement. So non-complemented subspaces. So in this particular case, you cannot have this kind of decomposition. So yeah, we want to go into this direction where we don't have necessarily a complement. So this is a version with complement, but as I said, is not the more general one. So you suppose that you have a quotient space. I call it S, like shape space. So this is, for instance, a space of 2D genus 0 surfaces in R3, which is a quotient space of a pre-shaped space like F by a group G. So F in the slides before was a space of parametrized surfaces, and G was a group of reparametrization, the homomorphism of S2 in the case of 2D surfaces. And you want to endow this shape space with a Riemannian structure. And you suppose that on the total space F, there is already a Riemannian structure with good properties. And the properties are the following. You suppose that there is a Riemannian metric on the total space F, which is G invariant. And so such that the tangent space of the total space splits. So this is a condition that is needed in the infinite dimensional setting to get this kind of simple version of the theorem, let's say. So you have a split kernel of the projection. So the total space of the tangent space of the total space F splits into the kernel of the projection, which is a direction of the fibers, and orthogonal complement. So if the metric is G invariant, then it induces a metric downstairs on the quotient, and such that you get an isometry when you restrict your projection to this orthogonal space to the fiber. So I would like to draw a picture because that will be probably a good thing. Actually, I would like to draw 4 pictures. I will draw it like. So the setting is the following. You have a quotient space here. You can, an element in the quotient space is a class. Above it, there is an orbit. You can single out some element here. That's a general setting. And you want to, what you're interested in is a Riemannian structure downstairs. Because as I said, we want to measure deformation of shapes irrespective of the parameterization. So up here are parameterized shapes. Down here are 2D, for instance, 2D manifold without parameterization. So the first way to put a Riemannian metric downstairs is a usual Riemannian submersion theorem that you see here. It's fine. So in this case, you suppose that you have a Riemannian metric upstairs on the total space F. So you know how to measure things here upstairs, and you want to get a Riemannian structure on the quotient space. So first of all, it should be independent of the way you will lift. So if I choose a representant in my orbit here and another one there, if I lift these 2 vectors, the scalar product should be the same. So this is the first condition. The Riemannian structure upstairs should be G invariant. Here I made so I made the hypothesis that the vertical space, which is the tangent space to the fiber, has a complement. So orthogonal for this Riemannian metric. This is what is called the horizontal space here, or kernel of GP perp. This is this space. So in this case, you get isometry from the horizontal space to the tangent space on your quotient by this procedure. So this is a first way, and very well known. And this is the way that was extensively used in shape analysis, but there were problems for using this method because it is still used actually, but it's very costly because there is a lot of information that you use unnecessarily because you're interested in the quotient. And remember, the fibers are the orbits under the group of reparametrization, which is infinite dimensional. So there is an infinite dimensional direction that you don't care, but you're still using it in this procedure. So I would like to present 2 different approaches to avoid this infinite dimensional direction. So the one that I called Riemannian metric induced by a smooth section, or Riemannian immersion theorem. Oh, I should mention that this is a joint work with my collaborator Steve Preston, and you can have the reference here. So the second method is the following. So this is not always possible. This is not always possible, but in some cases it is, and when it is, it can be very computationally efficient. So suppose that your fiber bundle is trivial and that you have a global section. This is, for instance, the case in for curves. I was mentioning that you have a arc length parametrization gives you a globally defined section. So I call S is this section, and then your quotient space actually can be identified with this section. So in each fiber, you have a preferred element. So undoing the quotient space can be done by undoing this section with a Riemannian metric. And then, if you start with any Riemannian metric upstairs, you can just restrict it to your section. You suppose this section is smooth, of course, to be able to restrict a Riemannian metric on it. And then what you get is that downstairs, the Riemannian metric will be defined as the projection of this, as an isometry of the tangent space to this section with the tangent space of the quotient. For instance, for curves, the section I said, you can take arc length parametrization. This is a smooth submanifold in the space of all parametrized curves. And if you start with a Riemannian metric on the space of curve of your choice, you can restrict it to this space, to this manifold of arc length parametrized curve. And this gives you a way to deform any shape. This is exactly this. So that would be the second way. And you see that here you avoid having an infinite dimensional unnecessary direction, because you choose your represented at each step. Of course, you can, if your fiber model is trivial, you can also take another section. If you start with a Riemannian metric on the total space, if you restrict it to another section, you will get another induced Riemannian metric downstairs. There's no reason it should be the same, right? So different ways, different choice of section will give you different Riemannian structures on the quotient. Are there questions here? Is it more or less clear? Okay. So now I go to the third case. So third way to induce a Riemannian structure on this quotient space. I'm doing this for Riemannian structure, but you can do this for any kind of geometric object, actually. Anyway, so for so again, you're just interested in the quotient, and here you will suppose that you have a preferred, should be here, a preferred distribution on the total space that is transverse to the fibers. What I mean is, you suppose that you have a complement to the fibers, and that these complements behave well with respect to the group action, meaning that if I act with a group element from the group G, then this group element will map one transverse to the other. So in this case, it's enough to specify the scalar product on vectors that are in this complement. And in the direction of a fiber, you can choose 0. And so the fiber will be in the kernel of this, of a bilinear form. But the bilinear form will induce a Riemannian metric on the complement here. And all of this has to be, of course, invariant by the group. In this way, you get a Riemannian structure downstairs, meaning non-degenerate definite positive. But upstairs, you have a 0 cost in the fibers. Okay, so this is a bit different from here, where you have a cost in the fibers. And in particular, for the, if I join two points here, well, it will depend on the endpoint here. The length of the curve will depend on the endpoint. Only horizontal curve will be mapped to geodesic downstairs. And here, it's a bit different because you have zero cost in the fiber. So if you lift a curve downstairs, you can lift it in different ways. But because the direction in the fiber has zero cost, you will end up with the same length. Okay? So this is very good for application because you can reparameterize your curve, your shape as you want, even during the minimization algorithm, without affecting the results. Other questions? No? Is it clear, more or less? Okay. So I'll go give you some examples. So I was mentioning the example of curves. I was mentioning the fact that arc-length parameterized curves define a smooth submanifold in the space of parameterized curves. This is a, very natural result, actually. So here there are two notation. I restrict to length 1 curves. So this is the C1, means curve with length 1. And inside of these, so C1 here, inside of these, the ones that are parameterized with arc length, meaning the velocity vector norm equal to 1. This set of arc length parameterized curve sits inside C1 as a smooth manifold. And of course, you know how to reparameterize a curve with arc length. There is a very easy procedure to reparameterize by arc length. But in fact, to be able to show that the space of arc-length parameterized curve is diffeomorphic as a quotient space to this quotient of parameterized curve by the group of reparameterization, because it is in a Fréchet setting, we need Nash-Moser theorem for this. So it's a bit, how to say, technical, but not difficult. So in this paper with my collaborator Steve Preston, what we have done is the following. We were starting with general Riemannian metrics, two parameter Riemannian metric on the space of parameterized curves. So A and B are two real parameters. We are on a space of curves parameterized from 0 to 1. And you integrate from 0 to 1 these quantities. Here you see there is the velocity of the parameterization here at the end. And we want to define a Riemannian metric there. So a scalar product on tangent vectors. So what are tangent vectors to a curve? Tangent vector to a curve will be a vector field along a curve, that's the W that is in the formula. So this is a function with values in R3, and there are two derivatives. R2, sorry, these are plane curves, so R2. So there is naturally the tangent vector to the curve is parameterized. Unit tangent vector to the curve, I should put some colors, perhaps. Well, okay, forget the colors. Yeah, thank you. So the tangent vector to the curve and the normal vector. So this is, the V is the tangent vector, the N is a normal vector. And so you can differentiate the W along the curve. This is this dsw, and look at the contribution along the curve, so in the direction of the tangent vector, or normal to the curve. And you can put different parameters, A and B, on this, two components. So one refers to bending and the other one refers to stretching. So along the curve, this will be the stretching so the effect of stretching that your tangent vector do on your curve. And the component normal to the curve will be the bending contribution. So you can put different parameters on stretching and bending. And this defines the Riemannian metric actually on curve module translation, to be more precise. So on the total space here. So this is in this setting. So this is a two-parameter family of Riemannian structure here, GAB, which is well behaved. So you can go to the quotient, and this family of Riemannian metrics will descend to the quotient and give you a quotient Riemannian metric. And of course, if you start with the same Riemannian metric, GAB, but you restrict it on the space of arc lengths, let's say, arc lengths, parametrized curve, then it will give you another Riemannian metric downstairs, right? There's no reason that it will be exactly the quotient metric. And actually, it is not. So what we did here is we took the quotient Riemannian metric and we pulled it back to the space of arc lengths. So how to do it here? I should use this one because I just want. So here you have the space of the tangent space to the space of arc lengths. And by the Riemannian submersion procedure, you get a quotient Riemannian metric, so you know how to, so I get one of these GAB metric on the quotient. So I have it here on the quotient. So I would like to write it as a metric on the space of arc length parametrization. So I need to be able to lift two tangent vectors on the quotient to this tangent space of arc lengths. And the scalar product of the lift will be the scalar product of the quotient elements. So this is what we did. We pulled back the quotient Riemannian metric to the space of arc lengths. And this gives us some equations that we were able to solve. So perhaps I should, yeah. Well, that's one way to relate this different procedure, let's say. I should mention that if you start with a Riemannian metric on the quotient, you can lift it in many different ways for these three different methods. I should add that for the method with a section, of course, you need that your bundle is trivial to be able to have a global section. Otherwise, you can just locally define a section and do something locally, which is also used in application, actually. If your section is defined almost everywhere, then you can still use it in applications. Okay. I wanted to briefly mention curvature length parametrization. I was mentioning here arc length parametrization. I said that there are many different possible parametrization. Curvature length parametrization is one of these. So how do you do it? Well, you take a curve and you compute the integral of the absolute value of the curvature along the curve. So because you take the absolute value of the curvature, this is positive, you integrate along the curve, you will get something increasing with your parameter. This is exactly what I'm displaying here. So this is the integral of the curvature along the curve. So here I'm starting, I don't know where exactly, at the bottom, I suppose. Here there is a lot of curvature, very steep. This is a moustache of, this is a profile of Elie Cartan. We have seen this picture. we saw this picture before, right? Yeah. So this is a moustache here, where a lot of curvature, then here a negative curvature. This is the sine curvature here. Okay, so you have this increasing function along the curve. And if you space your points so that you have a equidistribution of this quantity along the curve, you will get curvature length parameterization. So there will be a lot of points where there is a lot of curvature. So here you see the steepest ascent will be decomposed into different points. This is here on the left, equidistant spacing for this integral of curvature. So steepest ascent, a lot of curvature mean a lot of points. This corresponds here to this cluster of points on places where there is a lot of curvature. On the other hand, where there is no curvature at all, so it's at least almost straight lines, there will be no point at all. So you will not put points on straight lines, which is very useful in application because your information is concentrated where it is useful. So you need a lot of points where there is a lot of curvature. You don't need points at all when you know that you will just join 2 points by a straight line. So it's very convenient for sparse encoding of curves. Yeah, you can have a lot of different sections here. So here you see it's a Statue of Liberty with different parameterizations. On the very right hand, you are equidistant points along the curve. This is arc length parameterization. Here on the left, you have curvature length parameterization, points only where there is a lot of curvature. And of course, you can interpolate between these by integrating a constant plus the absolute value of the curvature along the curve, and you will get this kind of parameterization. So a lot of possibilities. So yeah, I mentioned curve arc lengths. This would be for this kind of integral, where the constant is exactly the length of the function. So you do exactly the same, and you get a parameterization which is in between arc lengths and curvature lengths. So different parameterization may be useful for different applications. And actually, any strictly increasing function along your curve will give you a preferred parameterization. And this is the message I would like to say here. So depending on your application, perhaps there is a increasing function that is natural. I don't know. With respect to the elasticity of your material, for instance, then you can take the integral of this absolute or this function, and you can reparameterize your curve respectively. And this is will be a good parameterization for your application. I go back to surfaces. So I mentioned for this second procedure to define a Riemannian metric on the quotient space, we need a global section. What about surfaces in R3? Is there a global section? What do you think? Yes, no? Do we have something analogous to arc length parameterization for surfaces? Not really, right? We have something which is not bad, but I mean, these surfaces, as I said, are genus 0, so these are Riemannian surfaces embedded in R3. These are complex surfaces, simply connected. So you know they are conformally equivalent to this unit sphere. So you have a preferred homeomorphism from the unit spheres to this surface, for instance, this hand, because of the existence of a complex structure coming from R3. This complex structure is depicted here. The blue arrow is a normal vector to the tip of the toe, of the finger, and you know how to rotate a vector, so you have a complex structure induced by R3. This gives you a natural complex structure on your hand, on your surface. So you know that you have a uniformization map. However, this is unique only if you fix 3 points on your surface. So modulo PSL2C, you have a better parameterization of a surface. So you can really, there are algorithms to get this using circle packing and things like that. However, they are computationally very, very demanding. So if you want to compare a lot of shapes, it will not be very efficient, let's say. But in theory, it's quite interesting anyway. So this is why the third approach, gauge invariant approach, can be used in this setting. So here you avoid the infinite dimensional direction that you don't care about. You don't have a section, or the section is difficult to compute. So you can use the third algorithm. This is what we did with my collaborator, Driha, Daoudi, and Srivastava. And there is a paper also in Notices of AMS with this idea. So what you get is, for instance, from a shape, a parameterized shape to the same shape with a different parameterization, like for these two hands, exactly the same shape, but the parameterization is completely different. If you join these two parameterized shapes by a curve, well, the length of the deformation will be 0 because it's in the vertical direction. So no cost on the fiber give you this kind of 0 energy path. Okay, so I think I'm more or less done with my time. Yes, I think so. So these are some references, and thank you for your attention.